Today we're going to start chapter 3, which is exponential and log functions. The first section is exponential functions, and that's what we're going to talk about today. An exponential function is a function with the general form y equals ab to the x. Now, there are a couple of restrictions on what these values can be. A can't be 0, because that would make the whole function be 0, and then that wouldn't be exponential. B has to be greater than 0, so B has to be positive. And that's the base number here of the exponent. So exponential functions don't work if that number is a negative. And the last restriction is that B can't be 1. And that's because if B is 1 and we took it to any power, it would just be 1 and it wouldn't be an exponential function anymore. So we're going to start with a graph, and we're going to graph y equals 2 to the x. So we're going to make a parent graph table for 2 to the x. So when you're graphing 2 to the x, you should have these numbers on your table. -3, -2, -1, 0, 1, 2, 3. So these should be the values that you have in your x column. Y equals 2 to the x. So now we'll plug in these values, and it will be a little painstaking at first, but you'll get really quick at it. So even though it starts up here at -3, I actually plug in the 0 first because that's easier. So if I put 0 in right here for x, I get 2 to the 0, which is 1 because anything to the 0 power is 1. Now let's put in 1 for x. 2 to the 1 is 2. 2 to the 2 is 4. And 2 to the third is 8. Now, when you use a negative exponent, like -1, that's 2 to the -1. Hopefully you remember that negative exponents turn numbers into fractions. So 2 to the -1 equals 1/2. So what does 2 to the -2 equal? Well, that's 1 over 2 to the 2. And that's 1 over 4. Now, hopefully you notice that when you use the negative exponents, it just takes the answer you have from the positive exponent and flips it upside down. So that can make filling out the table, wow, even more, or even easier. So 2 to the -3 then would be 1/8. Okay. So now we're going to plot these points over here on our graph. And just like I started the table with 0, 1, I'm going to start my graph with 0, 1 first. So here's 0, 1, 1, 2, 2, 4, 3, 8. And then I'll come back and do the negatives. So -1, comma, 1/2, -2, comma, 1/4, -3, 1/8. And so now we can graph this. Oh, that's a little wavy, but that's okay. Okay, so one thing to note is that no matter what exponent we put in here for x, I am never going to get a negative number as an answer. So what that means, I'm also never going to get 0. So there is a horizontal asymptote here at y equals 0. And we draw that in just like we did with rational functions way back in the beginning of the year. Okay, let's try this example. Y equals 1/3 to the x. Okay, we're going to start with the same x values we started with on the other table. And if it turns out that we're not going to use one of them, that's fine, but these are good numbers to start out with. So again, let's start with the 0. So 1/3 to the 0 power is 1, because anything to the 0 power is 1. 1/3 to the first power is 1/3. 1/3 to the second power. 1/3 to the second power is the same as 1 squared over 3 squared. So that's 1/9. And 1 over 3 cubed would be 1/27th. And just like in the first example, the negative exponents flip the answers from the positive exponents. The same thing happens here also. So 1/3 to the negative 1 actually equals 3. And 1/3 to the negative 2 equals 9 and 27. And if you are suspicious of that, then, you could always type it in a calculator. So let's graph these. And again, we'll start with the 0, 1, because that's the easiest point. I guess it doesn't matter. So 1 comma 1/3, 2 comma 1/9, 3 comma 1/27. Just like in the previous problem, it's not going to ever touch the x-axis. Right here we have negative 1 comma 3, negative 2, 9. And this one isn't going to fit, so I'm just not going to graph that one. And that's fine. Sometimes you just don't, use all the values. So you want to bend your graph, and you want to make sure that you're trying to avoid the x-axis. Definitely don't cross the x-axis on an exponential graph. Okay, so down here we're just going to make some notes about some things that we saw. So exponential graphs. So they do not intersect the x-axis unless there's some sort of shift. And that creates an asymptote of y equals 0, because that's the equation of the x-axis. Okay, b. b is the number that's being raised to the power. So in this case, b is 2, and over here, b is 1/3. So if b is greater than 1, like in the first example, then this is exponential growth. Because as you're traveling on the graph from left to right, you are increasing, so it's growing. If b is between 0 and 1, like a fraction, like over here in example 2, then as you travel on the graph from left to right, you are decreasing, and so we call that exponential decay. The domain of both of these is all real numbers because they continue on left and right in both directions. And the range for both of these is 0 to infinity. It never reaches 0, so that gives us a parenthesis, but they do go up forever. Excuse me. And so infinity. The y-intercept for both of these is 0, 1. But I would like to point out to you that it's not really just 0, 1. Come up here and look at the top where it says the general form is y equals ab to the x. This is really the y-intercept. The y-intercept is really 0, a. So that's what we're going to write down here. Y-intercept is 0, a. And this is just a note that y equals 2 to the negative x is the same as 1/2 to the x power. These are absolutely equivalent. And that's because 2 to the negative x could be written as 2 to the negative 1x. And that could be written as 2 to the negative 1 to the x. Because power to a power you multiply. And 2 to the negative 1 is 1/2. So these are equivalent here. Okay, next we're going to work on some transformations of exponential graphs. So we'll take the example y equals 3 to the x plus 1. Every transformation rule that you have already learned still applies and in the same way. Remember that changes to x always happen opposite. X's lie. So make a parent graph table and then apply the transformations. So we're going to make a parent graph table actually for y equals 3 to the x. And then we will apply the transformations to that. Now, 3 as the base of the exponent, because it's bigger, we'll wind up being able to put fewer points on our graph. So we can just start this one at -2. Because 3 to the third is 27, and that's not going to fit. So I'm just going to not do that one. And again, we'll start with the 0. So 3 to the 0 is 1. 3 to the 1 is 3. 3 to the 2 is 9. And the negative exponents will be the answers to the positive ones, but reciprocal. Now, if you remember from our transformation rules, this is a change to x, but whatever happens to x happens backwards. So if it says +1, we know that really means we're going to subtract 1 from all of our x's. However, that's going to be logistically difficult just because the x is already, it's on the left and, it already has this line in the way. So subtracting 1 from x is the same as adding -1 to x. So that's how we're going to write this. So we're going to add -1 to all of the x values. And we'll write our new values over here. So -2 plus -1 is -3. -1 plus -1 is -2. -1, 0, 1. And now these are my new x values that I'm really going to use. And nothing happened to the y values, so they're going to stay the same. Okay, so I'll start with the middle. So -1, 1. Then we have 0, 3, 1, 2, 1, 9. I was like, that 2 does not make any sense. Okay, and then -2, we have 1/3, and -3, we have 1/9. And we still have our asymptote here on the x-axis, so please draw that in with a dotted line. Okay. All right, let's try a different transformation. Let's try 2 to the x minus 3, but notice where is this -3? It's not up with the exponent. So this is going to be a vertical change, so a change to y. And what that will do is it will take all of your y values and subtract 3 from it. So let's start with our parent. This is a 2 to the x graph for the parent. So I will start with -3 because that fits. Well, I think it'll fit anyway. And then we'll put in the 0 if you don't have them memorized yet. So 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the third is 8. And then the negative exponents will have just the reciprocal of their positive exponent friends. Okay, so we decided that we were going to subtract 3 from all of the y values. Okay, I'm not going to start with the 1/8 because that's annoying. So let's come down here to the middle. 1 minus 3 is -2. 2 minus 3 is -1. 4 minus 3 is 1. And 8 minus 3 is 5. Now let's go back to the fractions. It's a little annoying because it's a fraction minus a number, but you're big people, you can handle it. So 1/2 minus 3 is -2.5. 1/4 minus 3 is -2 3/4. And 1/8 minus 3 is -2 7/8. So let's get these plotted. So 0, -2, 1, -1, 2, 1, and 3, 5. And then for our negative x's, we have -1, -2.5, -2, -2 and 3/4, -3, -2 and 7/8. Now you might be able to recognize here that it looks like this graph is getting closer to not the x-axis, but the line y equals -3. And that is true. The asymptote now is at y equals -3. Why is that the case? That's because of our vertical shift. So this shifted our horizontal asymptote. Let's go back up to where we made that list of characteristics, and let's add that in there. So right here, where we have does not intersect x-axis, asymptote y equals 0, this is only if there's no vertical shift. So if there's a vertical shift, that looks a little crazy, then that number is the horizontal asymptote. Okay. All right, let's try another example. Now this one has a multiplier. So the parent is 3 to the x. So I'll just start with the -2 because 3 to the third is 27. So that's kind of annoying. And we'll worry about this guy after. So here's the parent. 3 to the 0 is 1. 3 to the 1 is 3. 3 to the 2 is 9. 1/3, 1/9. And now this is a change to y. So this is a vertical stretch. It's also a vertical flip with this negative, but we'll take care of that all in at the same time. So we'll take our y values and we're going to multiply them all by -2. Oops, -2. So 1 times -2 is -2, -6, -18, -2/3, -2/9. So now these are all my new y values, and my x values didn't change. Okay, so notice that because this number got so big, I did change the scale here so that each block on the vertical axis really stands for 2. So the point 0, -2 then will really be here. 2, 4, 6, 8, 10. 1, -6, that will be over 1 and down 2, 4, 6. And over 2 down 18 will be here. Remember, we changed our scale. Over -1 down -2/3. That's pretty close. And even closer. With the fractions, you don't have to get that crazy about like exactly where they are. Notice there's no vertical shift here. So that means that our horizontal asymptote will remain on the x-axis, even though the graph flipped upside down. So there's an example of an exponential graph that's been reflected over the x-axis. Okay, let's identify exponential growth and decay. As we talked about up top, if b is greater than 1, we'll have exponential growth. And if b is between 1 and 0, basically a positive fraction, then it will be decay. And also to find the y-intercept. Remember, the y-intercept is 0, comma a. Okay, so let's look at this first one. Is this growth or decay? So we're going to look inside here. Is this less than 1? Yes. So this is decay. And because the b number is less than 1. The y-intercept is this number sitting out here. So the y-intercept is 0, 12. That's it. Okay, let's come over here. It's all about the exponential growth or decay is all about the b. It's about this number. It's about the number that has the exponent on it. This is greater than 1, so that makes this growth, exponential growth. This number determines the y-intercept. So the y-intercept is 0, comma 0.25. Okay. Let's look at this next one. It's also still under the directions of, identify if it's growth or decay. You put $1,000 into a savings account for 4 years. The account pays 5% interest annually. Is this growth or decay? Well, it's a savings account, so we hope it's growth. But how do we know this for sure? Well, first, savings accounts grow. That's what they do. But B would be 1.05. We'll discuss that more in a little bit. And of course, that's greater than 1, which makes it growth. And the y-intercept would be 0, comma 1,000. That's the amount you put in the initial investment. When time is 0, you've put in $1,000. Okay, this number here, B is called the growth factor. Or if it's less than 1, it would be a decay factor. I'll discuss that more in just a second. So what I'm going to give you now is a formula to calculate interest that's compounded annually. And that is A of t equals P times 1 plus R to the t power. Now let's discuss what all these things mean. A is the amount you have after the certain amount of time, or the final amount. T is the time that has passed. It's usually in years. It's interest, it's in years, but if it was not interest, if it was, something else that was growing, it could be, in a different amount of time. P stands for principal, but what that really means for us is the initial amount. Okay, 1 is a 1. R is the interest rate, but you do have to make it a decimal. And T is the time, and for interest, it's usually in years. Okay, so let's take our new formula here, and we'll try this problem. You invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will the account have in 6 years? Okay, so let's identify who's who here. First, we need our equation. Oh, I called it A here. Well, we'll just change it back to P. It doesn't really matter. The letters you choose are kind of arbitrary, but we'll make that a P for now. Okay. You invested $1,000. That's the initial amount. So that's the principal. The rate is 5%, but we need to make that a decimal. So that's going to be 0.05. Now, these are the numbers that are specific to our equation. Okay, this is sort of like the slope and the y-intercept, for the equation of a line. So, you find the slope, you find the y-intercept, you have the equation of one specific line, and then you can use x's and y's to find the other. So P and R are sort of like the y-intercept. Well, P is the y-intercept, but R is sort of like the slope. I mean, this isn't linear, but you can think about it the same way. T is like x. He's the independent variable. So like x, when you write a linear equation, you would leave the x there. So you're going to leave the t in the equation. For our purposes, for this question, t will equal 6. A is like the y. That's the dependent variable. And we're going to find y at 6. So this is the question here. So first, let's write the equation. So this one here, this is the general equation for an interest question that's compounded annually. Now we're going to write the specific equation for our problem. You remember, this is how we wrote equations when we were talking about variation. Remember, we had the general equation, we had the specific equation. So hopefully that was a good foundation for this. So this is our general nope, it's not. This is our specific equation for example 7. And then we're going to plug in the 6. So we're going to plug in the 6 for t. And with exponentials, you're going to, you need a calculator. So you would have a calculator nearby. So if you type this in, you will get 1340.10. And remember that this is money, so you need to round to the nearest, penny, the second decimal place. Now, interest doesn't have to be, that's an F. Interest doesn't have to be compounded annually. In fact, most of the times it's not really. So here's just some examples of other frequencies at which they could compound interest. So there's semi-annually. Semi-annually would mean 2 times per year. Quarterly, that would be 4 times per year. Monthly would be 12 times per year. And daily would be 365 times per year. Or, we could have weekly. That would be 52 times per year. And so on. Okay. If it's not compounded annually, though, you need yet another formula. And that formula is based on the one from up here, but it just is a little different because the interest isn't compounded once. It's compounded multiple times. So the difference here is that number of times the interest is compounded. So if you compare it to the equation from up here, you'll see it's pretty similar except for this n. And that n represents the number of times per year the interest is compounded. So we're going to write that down. Number times per year interest is compounded. And they're not going to give that to you in a number. They're going to give it to you in one of these. They're not going to say the interest is compounded 14 times per year. Like, that's just not something they're going to say. So you have to be able to read the words and then determine what it is, or how many times it's getting compounded. Okay, so let's take our new equation and let's do some more problems here. So you invest $500 in an account that pays 4.5% annual interest compounded annually. How much money will you have in 5 years? Well, it says annually. So the first thing we need to do is choose the correct equation. And that would be A of t equals P times 1 plus r to the t. You could use the n equation, but n would just be 1. So now let's make a list of the information we have. A of, no. Oops. We'll just keep that blank for now. P is 500, because that's how much we put in. R is 0.045. Time is the independent variable, but for us it will be 5. So I'm just gonna sort of go like that. And so we would be looking for A of 5, and we don't know what that is yet. So first, so this is our general equation. And now we'll write our specific equation for this problem. So that's going to be A of t equals 500, 1 plus 0.045 to the t. And now we can take this equation and take out the t's and put in the 5. But again, you need a calculator for this. So putting this in the calculator, we would get 623.09. And remember to round to the nearest 100th place. Okay. But what if the interest was compounded monthly? So using the same example, but then we would need a different equation. We would need the equation with the n in it. So that would be A of t equals p times 1 plus r over n to the nt. So I still have p equals 500. I still have r equals 0.045. But now I also have n, and that's coming from the monthly. So that's 12. And we're going to find A of 5. So our specific equation for this problem would be A of t equals 500 times 1 plus 0.045 over 12 to the 12t. It's really not important for you to simplify what's in here. That's not usually something anyone asks you to do, so don't worry about that. And our problem is asking us to find it at 5 years. So we're going to replace our t's with 5. And then we can type this in the calculator. And we're going to get 625.90. So if you compare that to the problem before, where the interest was only compounded once a year, you can see that it's to your advantage if the interest is compounded more frequently. So if it's compounded monthly, then you're going to wind up with more money at the end of 5 years. But there's something else. What if interest is compounded continuously? What does that mean? Okay, so if interest is compounded continuously, it uses another formula. And that formula is A of t equals P e to the RT. Well, what's E? E is a number, and that number comes from 1 plus 1 over n to the n power. So it's that equation. And as, this is supposed to, that's not an x, that's an n. And as n approaches infinity, this entire thing approaches this number e. Now, it approaches a number. Later, they called it e, but the e number equals 2.71828. Now, this is an irrational number, sort of like pi, in that it goes on forever with no pattern. So if you were to type this in the calculator and you were to put in larger and larger values of n, you're going to get closer and closer to this kind of bizarre number. But whatever. And this kind of looks like this, doesn't it? So if you compound interest more and more and more frequently, you can just forget this whole equation and just use this one, which is a lot easier. Okay, so we're going to use the same information from above, but we're going to compound the interest continuously. So that's the word that you need to look for to determine that we need this equation. So it's all in the words. Okay, let's write down what we know. We still want to know a of 5. That's what we want to know. P is still 500. The rate is still 0.045. But that's all we need to know. So let's write our specific equation. This is our general. So our specific equation is A of t equals 500 e to the 0.045 t. But we're going to replace our t with 5 because we're using the same equation from above, just the interest is compounded differently. So A of 5, if we type this in the calculator, is 626.16. And it's interesting that it approaches like a number. So you get more money the more frequently the interest is compounded, but like only up to a certain point. And so this is as good as it gets. You know, you're never going to get more money than that after 5 years unless you change something else, like the interest rate or how much money you put in. But 626.16, that's the limit. Okay, E, on your calculator, and I can show you this in class also, but you're going to want to know it for the homework. So there are 2 places you can get the E button. So the LN button is next to the 4. And in blue above the LN is E to the X. So you would hit second and the LN button to get E to the X. And so what that does is it prints in E, and then it gives you the little box for the exponent for you to put it in. If you just wanted E and you didn't want an exponent, then that is above the division sign. So here's the division sign over on the right side, and above that is just a single blue E. And if you hit that button, so second division, the calculator will just print the letter E, but it knows that this number is 71828. So that's where you're going to find your E. So give the homework problems a good effort, and I will see you.